Okay, we're coming to the end of Chapter 2 in the trigonometry textbook. In this video, we're going to talk about some further applications of right triangles. So in the previous section, we learned about solving right triangles, and then we worked a bunch of real-life application problems that involve right triangles. So actual geometrical right triangles. We solved for like the diameter of the sun, heights of like Mount Everest, different applications where geometry was used, well, specifically trigonometry was used to solve for lengths that were either difficult or impossible to measure, but with lengths that you can actually measure, along with devices that can determine angles between features. So you have certain lengths and certain angles, then you can solve for unknown lengths using trigonometry. And so now in this section, we're just going to look at some more real-life applications of how right triangles or solving right triangles are used. Okay, Johann Miller, known as, I guess that's Regiomontanus, shown here, was a 15th century German astronomer whose best known book is On Triangles of Every Kind. He used the recently invented printing process of the Gutenberg to promote his research. In his excellent book, Trigonometric Delights, Eli Mayor writes, so Eli Mayor wrote this in his book, Trigonometric Delights, Regiomontanus was the first publisher of mathematical and astronomical books for commercial use. In 1474, he printed his Ephemerides, tables listing the position of the sun, moon, and planets for each day from 1475 to 1506. This work brought him great acclaim. Christopher Columbus had a copy of it on his fourth voyage to the New World and used it to predict the famous lunar eclipse of February 29, 1504. The hostile natives had for some time refused Columbus's men food and water, and he warned them that God would punish them and take away the moon's light. His admonition was at first ridiculed, but when at the appointed hour the eclipse began, the terrified natives immediately repented and fell into submission. Interesting. So yeah, geometry and trigonometry are both really useful. And we saw that in the previous section with those example problems. But, there's just different applications where, and not just like surveying, but in engineering and in any field where geometry can come up, geometry or trigonometry. Not so much astronomy, I guess, but astronomy seems to be kind of in its own niche. But so yeah. Now, one thing we're going to focus on in this section is bearing. So we now investigate navigation problems. So like how ships navigate. And the reason we're going to do this, and I considered potentially skipping this, but these kind of examples are I think they're really helpful at giving you a sense of applied trigonometry. It's like we worked a bunch of examples in the previous section, and even though it's going to take a little bit of effort to understand what bearing means, I think once we learn it and work some example problems, you'll really expand your intuition behind applied trigonometry. So I think it's worth the effort. Okay, so we now investigate navigation problems. Bearing refers to the direction of motion of an object, such as a ship or airplane, or the direction of a second object at a distance relative to the ship or airplane. So bearing is just the direction of motion of a ship or airplane. What is that ship or airplane's bearing? Or you can think about bearing as the motion of a ship or airplane relative to another ship or airplane. We introduce two methods of measuring bearing. So how do you measure bearing or like express the bearing of a ship or airplane? So when a single angle is given, it is understood that bearing is measured in a clockwise direction from due north. Okay, this is one method. If someone tells you the bearing of, what's if you're in an airplane and you wonder what's our bearing, and someone tells you it's 15 degrees, well, that means you can think about it as measured 15 degrees clockwise from due north. And so an angle given like this, a bearing given like this, can be anywhere from 0 to 360. I'm assuming you wouldn't give anything greater than 360. Yeah, probably not. So it's just you're going to be given any angle between 0 and 360, or maybe negative angles, but I mean, we're not getting into this that deeply. Okay, a correctly labeled sketch is crucial when solving applications like those that follow. Some of the necessary information is often not directly stated in the problem and can be determined only from the sketch. Yeah, good problem solving tip there. All right, radar station A and B are on an east-west line. Okay, on an east-west line, and they're 3.7 kilometers apart. So you can draw the station A and B radar station, and they're 3.7 kilometers apart. Draw the east-west line and the distance of that line. Station A detects a plane at sea on a bearing of 61 degrees. Station B simultaneously detects the same plane on a bearing of 331 degrees. Find the distance from A to C. So, you can see how it's nice to not only know trigonometry but general geometry, and you can, if you also combine like good geometry skills with your trigonometry skills, then it really opens up the door to solving a lot of problems like this. But so station A detects the plane at sea on a bearing of 61 degrees. So a bearing of 61 degrees, that's measured clockwise from due north. There you go. Okay. And then station B simultaneously detects the same plane at a bearing of 331 degrees. So that's going to be, it's 29 degrees counterclockwise from due north. Okay, now if you make these lines here, like you draw a line from B to C and then from A to C, and then if you can take 90 minus 61 and get 29, and then you could take 90 minus 29 and get 61, and 29 plus 61 is 90, so this is a right triangle. But what you can think about is that's just they set up the problem that way to where that this results in a right triangle. In general, you won't have a right triangle necessarily. So that's what it's nice to know. In that case, you need just general geometry skills. And I'm going to eventually post a full course in geometry. So if you're in engineering, that's definitely a great course to go through. Or maybe you're in college and taking geometry, and so you should absolutely lean on that course to get to pass or get an A in that course. So yeah, I mean it's the question is asking for the distance from A to C. Well, you just use these bearings to construct this right triangle, and you have these angles to solve the right triangle. You have this distance, you've got two angles, so they did cosine of adjacent. So this is the hypotenuse across from the right angle. So they did cosine of adjacent over hypotenuse and solve for B, and that's it. Okay, and a second way to express bearing is, it says start with a north-south line and use an acute angle to show the direction, either east or west, from this line. Okay, figure 31 shows several sample bearings using this method. Either north or south always comes first, followed by an acute angle, then east or west. So, like, this is a bearing. These are a different way of expressing bearing, and it says so it's always going to start with north or south, and then from there you use an acute angle to show the direction, either east or west, from this line. So, yeah, this is pretty cool. So you start off by specifying north or south, and you can see what that means. It's you're specifying which, a north or south line that you're starting from, and then you say an acute angle east or west, and that means it's going to be here it's east of the north line, here it's east of the south line, here it's west of the south line, etc. Okay, so here's an example with that method too. A ship leaves port and sails on a bearing of north 47 degrees east for 3.5 hours. It then turns and sails on a bearing of south 43 degrees east for 4 hours. If the ship's rate is 22 knots, nautical miles per hour, find the distance that the ship is from the port. So, I'm sure they've set up the numbers to where we're going to end up with a right triangle, but I'm going to stress that in general that's not the case. That you always end up with right triangles. But so what are you going to do? You're going to put a starting point, okay, here's let's see, we're going to be going east, North, 47 degrees east. So let's do this. So it's north and then 47 degrees east. So this is like, it's something like this. You know, and it does that for, it sails that way for 3.5 hours. And what you would do is you would say a knot is a nautical mile per hour. So you would multiply 22 nautical miles per hour times 3.5 hours to get the nautical miles, and that's the length of this line. But then you put the angle, you know, I don't know which angle we're going to use yet, but it's so this angle is 47 degrees, and this angle would be 43 degrees. Okay. Then it says it turns and sails on a bearing of south 43 degrees east for 4 hours. So south 43 degrees east. So it's 43 degrees from the lower the south vertical. So, you know, I guess something like that. Okay. And yeah, you just want to get your angles right. So, you know, I didn't draw it that well. They have it better here. So like this is 47 degrees, and then this is 43 degrees, and then it ends up being a right triangle, you know, which is a coincidence. And so that's how you solve it. And you solve for, what's the question? This distance, AB. This is going to be the hypotenuse, and so yeah, there you go. I mean, we're going to work a bunch of example problems. You'll get a feel for this. So, okay, more applications. It says using trigonometry to measure a distance. The subtense bar method is a method that surveyors use to determine a small distance d between 2 points, P and Q. The subtense bar with length B is centered at Q and situated perpendicular to the line of sight between P and Q. Angle theta is measured and the distance d can be determined. So, okay, what's going on? The subtense bar method is a method that surveyors use to determine a small distance d between 2 points P and Q. So why wouldn't you just measure this with a tape measure? If it's that small of a distance, I mean, I'm not sure what. So this is P to Q. The subtense bar with length B is centered at Q. Okay. So maybe this distance isn't, it's small from a surveyor's sense, but not like tape measure small. So it's centered at Q, a bar with length B that is like tape measure length. You know this length well. You can measure that accurately. Length B is centered at Q and situated perpendicular to the line of sight between P and Q. Angle theta is measured, and then the distance D can be determined. So they can use a device to get that. They've got the bar set up. And again, we're going to work some examples, but I'm assuming that P to Q is not that short from like that you can measure it with a tape measure. Maybe it's like across like a field, like a big field, like a farmer's field or something. So you've got a bar here, and then you can you can walk to the other point and then use the angle measuring device, and you've got the two ends of the bar, and you can get this angle here, this included angle between the ends of the bar. You know the length of the bar. And so with that, what's the distance D between P and Q? Well, since the bar is centered here, then you can drop a bisector, an angle bisector that's going to be perpendicular to this angle, and that's going to, because these two, this is the bar is like, the idea is P, it's this bar is perpendicular to the line of sight between P and Q. So this line of sight is the distance, it's perpendicular, and the bar is centered. Not only is it perpendicular to the line of sight, but it's also centered. So because of that, you know that the height of this triangle here, this is going to be a isosceles triangle, and this height is going to bisect this angle. So you can divide that angle by 2, and then you'll have a right triangle here. This B divided by 2, the height, and the angle, and you could solve for D. Right, again, it comes down to you have to have this bar it's centered at Q, and you've got this straight line distance between P and Q. It's centered at Q, and it's perpendicular to the line of sight between P and Q. That's the key. Because when that's the case, then when you get this angle here, angle theta, you know that the perpendicular, if you drop a perpendicular to the base of the triangle, you know that that's going to go to that center point, and it's going to bisect the angle. That's stuff we learn in geometry. Okay. Last example, solving a problem involving angles of elevation. Francisco needs to know the height of a tree. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. He then moves back 50 feet. From the second point, the angle of elevation to the top of the tree is 22.2 degrees. Find the height of the tree to the nearest foot. So yeah, I'm learning as we go through these problems that those devices you see surveyors using, they're really good at measuring angles accurately between features. And you can imagine even a feature that's a long distance away. So if you can get angles, as well as you can also measure you can measure certain lengths manually, like the length from the tree, or he knows he moved back 50 feet, then you can solve for these angles that are, or these lengths that are hard to measure. So, okay, he comes here and finds the angle of elevation. So that's the angle above the horizontal is 36.7, then moves back and finds that this angle of elevation is 22.2, and this is 50 feet. He moves back 50 feet. Okay, so how is this a trigonometry problem? Well, we know that this is going to be a certain right triangle. And I believe that would be, no, these aren't going to be, these wouldn't be similar, these two. These would not be similar because the angles are different. But you can, let's see, they call this length x, and then we know that this length is going to be x plus 50. So then you can say, like, the sine of 36.7 is the height over x, and the sine of 22.2 is the height over x plus 50. So you have like two equations and two unknowns, and you can solve for h and x. But to me, he could have measured what x was. So, but I think they're just trying to make this complicated so we can solve it. Okay, let's work some examples.